Welcome to This Explainer. Today, we're going to calmly dissect a really fascinating central argument that the absolute biggest shift happening in AI infrastructure right now is the transition to inference as the dominant, governing, operating load. For years, the whole industry was basically obsessed with training larger and larger models. But today, we're looking closely at why the physical bottleneck has fundamentally shifted and how architectures like Cerebras are attempting to completely rewrite the rules of compute.
So here is our agenda. We're going to cover the shift to inference, the physics of decode, the wafer-scale wager, the EP compute map, the contenders in the space, and finally, what we call the era of governed compute.
All right, let's jump straight into section 1, the shift to inference, from compute abundance to energy flow discipline. Okay, so the industry is aggressively moving away from a training era, one that really rewarded massive parallel computation, straight into an inference era. Think about it. Today, we have persistent agents, long context windows, multimodal systems, coding tools, and all of these endlessly multiply sequential token demand. When AI infrastructure was built around training, traditional GPUs won big because they're just fantastic at parallel matrix operations. But agentic AI, it loops across many turns. And that turns inference from what used to be just a marginal service cost into the central infrastructure battlefield. To really grasp this physical hardware bottleneck, we first need to define a term, prefill. This is the stage where GPUs absolutely excel, mostly because they can process large input contexts in parallel. It's kind of like reading the problem statement on a test. If you hand an AI a massive document, it can process a huge chunk of that sequence simultaneously. Because it's a parallel workload, the traditional GPU architecture is incredibly strong here. But then, in stark contrast, you have decode. This is a purely sequential process. And here, data movement, memory locality, and latency, not raw arithmetic, become your dominant costs. Decode is the AI actually producing the answer. Because autoregressive models generate one single token at a time, and the next token depends entirely on the previous ones, the system has to repeatedly access model weights and the key value cache state. So, the really crucial point to take away here is that for large models, the actual math is only a tiny fraction of the total time. The real cost? It's just moving the data around. Which brings us nicely to section 2, the physics of decode, a path and locality problem. Think of a traditional GPU having to repeatedly pull, say, 140 gigabytes of model weights from external memory just to generate every single token. The computation itself is lightning fast, but the physical path that data has to travel, it's a massive logistics bottleneck. I love the quote from the source material here. The chip may be a brilliant chef, but the ingredients are far away. Decode isn't primarily a calculation problem anymore. It's a path problem. The physical question we have to answer is, how close can the model state be placed to the compute cores? So let's look at section 3, the wafer-scale wager, attacking the decode bottleneck at the physical level. This is where Cerebras's architectural wager comes into play. They propose using a massive single wafer-scale engine to put the model state directly next to the compute cores, thereby collapsing that physical distance the data has to travel. Literally, instead of cutting many small chips out of a silicon wafer, they just use the whole entire wafer as one giant engine. By putting vastly more memory and compute onto a single physical substrate, they drastically cut down on cross-chip traffic and attack the latency penalty of inference head-on. Now, this creates a very clear boundary for workload fit. Small models run beautifully purely on chip, totally collapsing the physical distance data travels. This low latency is incredibly efficient for small models that are just running rapid inner-loop reasoning steps. But what about massive frontier models handling high-judgment tasks? For those, the system uses something called weight streaming. This requires incredibly strict planning to stream weights from external storage without ever leaving the chip idle. Let's move to section 4. The EP compute map, analyzing AI hardware as an energy system. To really evaluate this, the source material introduces an energetic paradigm, or EP compute map. This map strips away all the marketing hype and looks at 8 key components: the energy source, the physical path, storage, conversion from prefill to decode, loss points like memory stalls, control mechanisms, telemetry feedback, and deployment stability. It basically forces us to look past just a single benchmark number and evaluate the whole energy system. Are you losing valuable cycles to memory stalls? Is the physical path just too long? Are your control mechanisms robust enough to actually handle the speed? The core causal chain the paper argues is very distinct. Model state must move toward compute. Reduced movement lowers latency and loss. That lower latency then drastically increases agent throughput. But, and this is a big but,
ultimately, strict control determines whether that speed actually becomes useful work or just cascading instability. This is the heart of the argument. You have to bring the model state to the compute. But once you unlock that low latency, you suddenly have agents that can think, loop, and spend money much faster. That kind of speed absolutely demands strict control.
Next up, Section 5, the contenders, a landscape of conditional advantages. So rather than a simplistic zero-sum narrative where one company takes all, we actually see different physical approaches here. Cerebras leverages extreme wafer-scale locality. Grok relies on deterministic SRM scheduling for incredibly fast first token response. And NVIDIA, well, they dominate through ultimate flexibility and their deeply entrenched CUDA ecosystem. The source material is very clear about this. Cerebras is not guaranteed to just magically replace NVIDIA. NVIDIA still has massive advantages in developer trust and broad workload flexibility. The winner here depends entirely on the specific conditions and scale of the workload.
And this naturally leads us toward a future of heterogeneous infrastructure. I mean, if NVIDIA adopts SRAM-oriented inference, or if major cloud providers like AWS start splitting prefill and decode onto entirely different hardware substrates, it just completely validates that solving this decode bottleneck is the industry's absolute top priority. Think about it. A single inference request might soon be decomposed. Prefill gets routed to a traditional GPU, while the decode phase routes over to specialized wafer-scale or SRAM hardware.
All right, our final section, Section 6, the era of governed compute. Managing workload, financials, and stability.
At the end of the day, fast inference is a control problem. Accelerating token generation without governing context budgets, rate limits, and tool permissions, that simply accelerates budget burn and unsafe execution. If an AI agent executes tool calls at ultra-low latency, but it doesn't have a control layer capping its budget or validating its deployment authority, you really haven't built a useful system. Actually, scratch that. You've just built a highly efficient way to generate errors at scale.
And this need for control definitely extends to the financial narrative, too. Having a massive backlog of signed commitments means pretty much nothing if customer concentration, valuation pressures, or data center cooling burdens prevent actual deployment and revenue realization. A sky-high valuation and a great story about the inference boom have to be converted into physical reality. That means managing the intense deployment burdens of specialized infrastructure, like the intense liquid cooling and facility power capacity required for these massive systems.
When strategic customers like OpenAI or Meta sit down to evaluate new infrastructure, they bypass the simple benchmark speeds. Instead, they use a practical checklist that focuses heavily on sustained tail latency, model fit, and the actual real-world cost per completed workflow. It's not about how fast a chip runs a single isolated benchmark prompt. It's about how it performs under long-running agent tasks with high concurrency. Does the model even fit on the chip? How easily does it integrate with existing safety and data pipelines? Which brings us to the final overriding thesis of the source material. The fundamental unit of competition has changed. The inference era will be won not by peak compute alone, but by the architecture that best governs locality, memory, latency, scheduling, cost, and state movement. So, Cerebras may not replace NVIDIA entirely, but it really forces us to ask a big question. As specialized inference layers become critical, who will ultimately master the physics of governed compute? The shift to agentic AI pretty much guarantees that sequential token demand is only going to increase from here. Whether it's wafer-scale engines or clustered SRAM, the future of AI hardware belongs to architectures that don't just calculate fast, but intelligently govern the flow of energy and state. Thank you so much for joining me for this explainer. Keep questioning those bottlenecks, and I'll see you next time.